Hello all. It feels like I'm on the roll these past few days because I have been pumping out videos one after the other. So I hope these videos are useful. So today we're going to do a Unit 5 paper, okay? So it's the Unit 5 Thermodynamics, Radiation, Oscillations, and Cosmology paper from October 2025. So this is one of the most recent one actually, okay? And as I said in a previous video, there is also a Unit 5A. I don't know how different it will be from this one. But in the case of Unit 4, it was different. I mean, Unit 4A was different from Unit 4. So I will check it out. And if I manage to solve it soon, I might upload a video about Unit 5A. But the plan is to finish all these papers. So I'm going to do Unit 6 and then probably Unit 1, 2, and 3, which I haven't done before. Okay. And I have some thoughts about doing similar videos with just past papers from mathematics exams, okay? I mean, I haven't said this before, but as an undergrad student, I studied enough math to be considered a mathematician. So as I say, I'm a casual mathematician, but I think I can do it, okay? I cannot do chemistry. I mean, I probably can if I study too much, but I don't want to, So anyway, we'll see. So let's jump straight in, okay? I'm sorry for this long introduction. So, section A, this is the multiple choice section as always. And the questions are 1 mark, as I said a billion times before, and they shouldn't take you more than a minute, maybe 2 to solve, okay? So the rule of thumb, as I said in other videos, is that 1 mark means 1 minute, 10 marks means 10 minutes, more or less, okay? So that's the general rule. Okay. Question 1, which of the following is an example of a resonance? So, plucking a string on a guitar sounds promising, but no. Striking a tuning fork on a hard surface, I don't see why. Displacing a pendulum to one side and releasing it, that's actually just an oscillation. And D, pushing a swing each time the swing is at its maximum height. Okay, so this is the key word, maximum height. So that's an example of a resonance actually, okay? So you keep pushing at the maximum height and a resonance occurs. Question 2. The table gives the ionizing ability and penetration of alpha radiation and gamma radiation, okay? Which row of the table is correct? Okay, alpha radiation has low ionization. No, that's totally wrong, okay? So actually we know that alpha radiation has high ionization, so we can immediately go to options C and D, okay? And then for gamma radiation, we know that gamma radiation has low ionization ability but high penetration, so C is the correct answer, okay? Question 3, to avoid unwanted large amplitude oscillations in a machine, damping may be used. Which of the following statements about the damping force is correct? So let me see. It is always in the opposite direction to the acceleration. No, I mean, the definition has nothing to do with acceleration. So damping is actually in the opposite direction than velocity. So we know that the answer is B. Okay, so I'm not gonna read the other ones because the general rule is that damping is proportional to some constant, let's say B times the velocity, okay? So that's the answer. Moving on. Question 4. The Hubble constant is related to the age of the universe. A recent estimate of the age of the universe is 1.37 times 10 to the 10 years. So that's about 14 billion years. That's a long time. And if I am allowed to be philosophical, you know, the universe spent 14 billion years of existence. So we have an iPad in front of us and we are solving an A-level physics paper. Is this the best we can do? I think we can probably do better, but okay, this is what we have right now. Okay, I'm sorry, this was a really bad joke, I think. So let me know what you think. So anyway, okay, which of the following expressions gives a value for the Hubble constant in seconds to the -1? And they give you the duration of a year. Okay, So this is a strange question in that usually you know the Hubble constant and you use it to calculate the age of the universe, and that's done by using this formula, okay? And I'm pretty sure this is one of the formulas they actually give you. Let me check. Okay, this is unit 4, unit 5, okay. So, okay, astrophysics and cosmology. Okay, no, they actually don't give you that. They give you just the cosmological expansion. But, okay. So, yeah, they don't give you that. So you actually have to remember this, okay? So, the age of the universe is inversely proportional to the Hubble constant. So, H naught is simply 1 over T naught, okay? Where T naught is the age of the universe. So, we know that T naught is 1.37 times 10 to the 10 years, and then we have to multiply by 3.15 times 10 to the 7 to get this value in seconds. So the option, the only correct option is C. Okay, question 5. A mass is hung from a spring attached to a fixed support. The mass is partially submerged in a beaker of water as shown. Okay, you have the fixed support, the spring, the mass, and the beaker and the water. The mass is displaced vertically and released. Okay, which of the following best describes the oscillation of the mass after it is released? Okay, so this is pretty much the same, not the same, I mean, it's the same concept as question 3. So this is a damped oscillation, okay, because you have the water. So we can see an example here. So when the mass moves down, then the water pushes up, right? Because it provides resistance. Or in the opposite direction, like if the mass tries to move up, then the water pushes it down. Okay. So there is some resistance opposite to the velocity, so that's a damped oscillation. Let's move on. Question 6. Star X and star Y have the same luminosity. Okay, the distance of star Y from the Earth is d. When viewed from Earth, the intensity of star Y is 4 times the intensity of star Y. Sorry, the intensity of star X is 4 times the intensity of star Y. Which of the following is a possible value for the distance of star X from Earth? Okay, so let's write down the intensity of the star X. That's going to be L over 4 pi d squared, right? And then, wait, let me see. Sorry, dx squared. Okay, let's call it dx. And the luminosity of star Y is L over 4 pi d squared, because they give us that the distance of the star Y from Earth is d. Okay, so now we know that Ix is 4 times Iy. So L over 4 pi dx squared is equal to 4 times L over 4 pi d squared. Okay, so this, I mean, most things cancel. So we can immediately deduce that dx is d over 2, where we take the positive root, of course, okay, because it's a distance. So the correct answer is B, okay? Right. Question 7. Star P and star Q are main sequence stars that are the same distance from Earth. The surface temperature of star P is greater than the surface temperature of star Q. Okay. Which of the following graphs could represent the two stars? Okay. Here you have to be careful, because notice that these graphs give you the frequency of radiation, which is unusual. Okay. And these two graphs give you the wavelength. Okay, so we know that in case we're given the wavelength, okay, if we focus on this graph C, we see that we know that the temperature of P is larger than the temperature of Q, okay? And the peak radiation is at a lower wavelength as expected, okay? So this it's obviously wrong. And if for these ones to be correct, so sorry, I got confused for a moment. So for A or B to be correct, we should have something like I don't know. Okay, the star P. So what I'm trying to say is that the reverse will be observed. So you would expect, if you use the frequency of radiation, the star with the highest temperature would have a peak at a higher frequency, okay, if you use frequency. I've never seen it done, but in case you wanted to work with frequencies, you should have something like this, okay? So, okay, so this is the intensity and this is the frequency. Then P should look like this, say, okay? And then Q should look like this, okay? So lower frequency means higher wavelength, okay? Higher frequency means lower wavelength. So P will be this guy and Q will be this guy, okay? I hope this makes sense, okay? I've never seen it done with frequencies though, okay? But that doesn't prevent them from asking you that way. So you have to be careful of what's written in the axis. Let's move on. Question 8. As the Earth orbits the Sun, the distance between the Earth and the Sun varies. As the distance varies, the gravitational force between the Earth and the Sun varies. The magnitude, okay, so that's important actually, the magnitude of the gravitational potential energy of the Earth also varies. Which row of the table is correct? Okay, to understand this, I'm gonna use a clean page to explain this. I'm sorry. I'm gonna use a clean page. Let's write down the gravitational potential energy of the Earth. So that's gonna be U equals to the mass of the Earth times the gravitational potential from the Sun, which is nothing more than ME. We need a negative sign, and then G M of the Sun over R, okay? So this is going to be minus G, the mass of Earth, the mass of the Sun over R, okay? But they tell us that we should work with the magnitude of the gravitational potential energy. So if we take the magnitude, we will simply have U equals to G ME M Sun over the radius of, the radius, yeah. So the gravitational energy is simply given by Newton's law, G times the mass of the Sun times the mass of the Earth over R squared, okay? So if I plot this thing, if I plot these two things, okay, so this equation 1, this equation 2, they will look very similar, okay? So let's use, actually, let me erase this, and let's use red, okay? So let me think. Okay, so this is going to be the magnitude of the gravitational potential energy, right? And the gravitational force will look like this. It will fall faster because it's 1 over R squared. Okay, but the bottom line is that okay, so this is the distance R between them, I guess. Okay, so what we see here is that okay, let's read off the table. So distance between Earth and the Sun. When the distance is least, the gravitational force is the greatest, and the gravitational potential energy is the greatest. Is that correct? Let me see. Yes, actually, right? Actually, that's the right answer. Sorry. Yes, okay. So this is the region we are interested in. If the distance between them is the least, then we're gonna have the maximum gravitational potential energy and gravitational force, right? So A is the correct answer actually. Then, okay, if the distance between the Earth and the Sun is least, the gravitational potential force is least, and the gravitational potential energy is least, it's obviously wrong, as you see from this graph, okay? So I hope this explanation works for you. If you have any questions, let me know in the comments. I always answer. So yeah, let's move to question 9. A 500 grams mass was hung from a spring. The mass was displaced vertically downwards by a small distance and released. The mass oscillated with simple harmonic motion of period t1. The 500 grams mass was replaced by a 250 grams mass, and the spring set into oscillation. The 250 grams mass oscillated with a period t2. Which of the following is the ratio t1 over t2? Okay, so we're going to use the formulas. So t1 over t2 is simply, so t1 is going to be 2 pi, then the square root of m1 over k, and then we're going to have 2 pi, the square root of m2 over k. Okay, 2 pi cancels, k cancels. So we're left with the square root of m1 over m2, and this is simply just the square root of 500 over 250, which is 2. So c, the square root of 2, sorry, which is c. Okay. A container is filled with a mixture of xenon gas and argon gas at a constant temperature. The mass of a molecule of xenon is 3 times the mass of a molecule of argon. Okay, which of the following is the ratio? And they give us that ratio, the square root of c squared for xenon and argon. Okay, so first of all, if you go in the back of your paper, but it's good if you actually remember some of these things so you don't have to spend time looking for the equations. So let's see. Yes, okay. This is the formula we need, okay? It gives you the average squared velocity for a molecule of mass m according to the temperature, okay? So let's go back over here, close this. So 1/2 times the mass of xenon times c squared for xenon. Okay, I'm using that subscript. It's gonna be 3/2 kT. Okay, and then we have 1/2 mass of argon times c squared for argon, and since they are at the same temperature, this is also gonna be 3/2 kT. Okay, so if we divide, everything to the right hand side is cancelled. This is cancelled, so we are left with mass of xenon over mass of argon times c squared for xenon over c squared for argon equals to 1. Okay, and now let's see. We have to take the square root of this thing actually. Okay, so I'm gonna do it in the next step. So c squared for xenon over c squared for argon is mass of argon over mass of right? Yes, mass of xenon, and we have to take the square root for both sides, right? Because this is what they ask us to find. So this is equal to the square root of 1 over 3, right? Because they tell us that the mass of xenon is 3 times the mass of argon, okay? So the answer is A. Okay, this was a little bit of a tough part A, I would say. So, section B, question 11. The closest planet to Earth outside our solar system is Proxima Centauri b. And if I don't feel lazy, I'm gonna try to find that video. There is this guy in Australia, I think he's a physics professor, maybe, I'm not sure. But he's in a park and he shows in the scale in which planets will be, the sun will be the size of a basketball. Okay, that's the idea. How far away would the planets be? Okay, and he shows the planets in that park in Melbourne. Actually, they actually did this. Like, I think it's an attraction of the park or something like that. So they show all the planets. Okay, so for example, if the sun is in the middle of the park, then I don't know, Pluto, if you take Pluto to be a planet, Pluto will be like a few hundred meters away from the sun. And then they actually have Proxima Centauri b, and you have to drive to the next town in that scale to find it. Okay, something like that. If I find the video, I'm gonna link it in the description and you can visit and see. So let's solve the problem though. I don't know why I'm so chatty today. So the closest planet to Earth outside our solar system is Proxima Centauri b. Scientists believe that the planet has a mass of 7 times 10 to the 24 kilograms and a radius 40% greater than the radius of Earth. Calculate the gravitational field strength at the surface of Proxima Centauri b. And they give you the radius of the Earth. So g is simply g times the mass of the object over r squared. By the way, you also have a g, like you can calculate the gravitational potential of yourself, if that makes sense. The gravitational potential, g, the strength, the field strength. So it's gonna be tiny. So, okay, r is the radius of the Earth plus 40% because it's 40% greater. So let's say 0.4 radius of the Earth, and 0.4 is of course 40%. Okay, I hope that's easy. Okay, and so this means that the radius is 1.4 times the radius of the Earth. So the radius is 1.4 times 6.4 times 10 to the 6 meters, which is 8.96 times 10 to the 6 meters. Okay, so g is going to be 6.67 times 10 to the negative 11, then times 7 times 10 to the 24 over 8.96 times 10 to the 6 squared. Okay, and this is in newtons per kilograms. I'm being lazy about writing all the units down, but if you reduce everything down to newtons, meters, kilograms, seconds, and so on, everything gets cancelled nicely. So the final answer is 5.82 newtons per kilogram. Okay, so one half of what it is on Earth. So I guess if you visit this planet, it's gonna be fun jumping around because you're gonna be, if you are as strong as you are here on Earth, if you jump, you're gonna jump twice as high. So I don't know if if you take an Olympic high jump athlete, those people jump like 2.4 meters. So in this planet, they're gonna jump 4 or maybe 5 meters. That's crazy. Okay. So question 12. On Earth, hydrogen is observed to emit a spectral line at a frequency of 6.9124 times 10 to the 14 Hertz. The same spectral line observed in the radiation received from the Andromeda galaxy has a frequency of 6.9149 times 10 to the 14 Hertz. Calculate the magnitude of the velocity of the Andromeda galaxy relative to Earth. Okay, so they ask for the magnitude, so you shouldn't worry too much about whether this is redshift or blue shift, but I'm gonna tell you the answer anyway once we're done. So this factor z is equal to delta f over the frequency in the lab, okay? And this is going to be equal to v over c, okay? I think you can call z as the Doppler factor, but I'm not sure. Okay, so v is equal to c times delta f over the frequency in the lab, okay? And as I said, we are interested only in the magnitude, so I actually did the calculation. Wait, and so c times f in the lab minus f observed over f in the lab. Okay, so that gives you 108.5 times 10 to the third meters per second, or 1.09 times 10 to the 5 meters per second. Okay, is this blue shift or red shift? So the frequency observed is larger than the frequency in the lab, right? Because this is the frequency in the lab and this is the frequency observed. So the observed frequency is larger, which means that the observed wavelength is going to be the smaller, right? But smaller means blue shift, right? So this is one of the galaxies that actually move towards us, okay? They're going to come and collide with our galaxy, right? Right. And I think this is bound to happen in a few, is it million or billion years? I think millions. I think in about 200, maybe, 2 million years, we can actually check. So, okay. So, let's check. So, Andromeda galaxy collision. Let's see. I don't have internet for some reason. So anyway, if I remember, I'm gonna list it later. So anyway, let's move on to question 13. A particle must have a minimum kinetic energy to escape from an astronomical object to a distance where the gravitational force between them is negligible. This minimum kinetic energy is equal to the gravitational potential energy of the particle at its initial distance from the astronomical object. Okay, so that's a key actually. So this sentence here is a key to this problem. So the velocity required for this minimum kinetic energy is called the escape velocity. And they give you the escape velocity, okay? And they ask you to show that the escape velocity is given by that expression. So the minimum kinetic energy is equal to the gravitational potential energy of the particle at its initial distance from the astronomical object. Or in other words, we have the gravitational potential energy is G times the mass of Earth. Sorry, times the mass of, it doesn't have to be the Earth, it can be any astronomical object. So G times M times the mass of the object over R. Okay, so that's the gravitational potential energy at a distance when the object is on that astronomical object. And the kinetic energy is 1/2 mv squared. And we have to set this equal to each other. So 1/2 mv squared is G capital M lowercase m over R. We can cancel the mass. And you immediately see that this is equal to 2 gm over r square root. Okay, easy peasy. Part B, Sagittarius A star is a black hole at the center of our galaxy. Nothing can escape from a black hole, not even light. Calculate the maximum radius of Sagittarius A star. Okay, so this is kind of a trick question. And okay, they give you the mass of the sun, and they tell you that the mass of Sagittarius A star is 4.3 times 10 to the 6 times the mass of the sun. Okay, so we can use this formula, right? So the escape velocity is going to be the square root of 2gm over r. Okay, but we need to find the r, the distance, like the radius of this black hole. Okay, so let's do some manipulation. So v squared is equal to 2, sorry, the square root goes away, 2gm over r. So let's convert this to r, like actually, let's write it as r. Okay, so r is 2gm over escape velocity squared. Okay, so they tell you what's the maximum radius of Sagittarius A. The maximum radius will be when the escape velocity is equal to c. Okay, so this is the trick because it's a black hole. Okay, so 2gm over c squared. Okay, why is it maximum? Because if we use a smaller velocity than c, then what's going to happen? Let me see. So wait, this doesn't make sense. Okay, is this correct now? Okay, I have to check. I have the solution in front of me, but I need to check the mark scheme. Give me a second. So I have a feeling that I messed this up for some. No, I didn't. Okay, this is okay. All right, so if we plug in numbers, this is 2 times 6.67 times 10 to the negative 11, and then the mass is 4.3 times 10 to the 6, and then the mass of the sun, which is 1.99 times 10 to the 30. These are really large numbers, and then we have to divide by the speed of light squared. Okay, so the answer is 1.27 times 10 to the 10 meters. Okay, and that's our answer. All right, let's move on to question 14. A spherical balloon has a diameter of 11.5 centimeters. The temperature of the air inside the balloon is 22 degrees Celsius. The balloon is placed in a beaker of hot water at a temperature of 95 degrees Celsius as shown. Okay. The temperature of the air in the balloon increases. To maintain a constant pressure of air inside the balloon, the diameter of the balloon increases to 12.3 centimeters. Deduce whether the temperature of the air inside the balloon becomes equal to the temperature of the water during the expansion of the balloon. Assume that the temperature of the water remains constant. Okay, so before writing down any numbers, let's write down some general equations. So the initial pressure times the initial volume of the balloon should equal the number of air molecules inside the balloon times Boltzmann's constant times the initial temperature. And then the final pressure, which is equal to the initial pressure, that's why I don't use subscripts, okay? And they actually tell us that to maintain a constant pressure, okay? So the pressure is constant, okay? So P times the final volume of the balloon is equal to N, the number of molecules, which is the same as before, so I don't use a subscript, times Boltzmann's constant times the final temperature, right? Now we can divide and get rid of many things here. So if we divide, P goes away, N goes away, K goes away. So VI over VF is equal to TI over TF. By the way, I think I said it in previous videos and in the lesson videos. In general, my tendency is not to plug in numbers until I reach a final expression algebraically. Okay, so that's why you usually see me arriving at the final formula and then plugging in numbers, and I do that on purpose because if you plug in numbers, it becomes a mess to deal with. Okay, so the final temperature is equal. I promised in previous videos to make it better, to improve my handwriting, so I'm trying. Okay, so the final temperature is equal to the final volume over the initial volume times the initial temperature. Okay, they give us the diameter. So, okay, I'm going to use a clean page. So, TF, what's the volume of a sphere? It's 4/3 pi, and then times the initial radius square, times the final, because this is V final, right? Times the final radius, but we are not given the radius, we are given the diameter, so the radius is equal to half the diameter, okay, cubed. And then in the denominator, we have 4/3 pi di over 2 cubed times the initial temperature. We also get nice cancellations here. So, so the final expression is dF over di cubed times the initial temperature. So we don't have to convert to meters in this case because we have 12.3 centimeters, right? And initially we had 11.5 also centimeters. So because centimeters and centimeters cancel, we can actually use centimeters in this case, okay? Cubed. I mean, if we convert to meters, that's gonna work as well, but it's an overkill. It's not needed, okay? And this is the part where you have to be careful because remember I said whenever you deal with temperatures, it's the safest is to convert to kelvins, okay? You don't have to convert to kelvins when you use the expression for thermal expansion, but it's safer to just convert to kelvins, okay? So the initial, so Ti is 22 Celsius, which is 273 plus 22, which is 295 kelvins, right? So we have to multiply this by 295. So we find 360.9 kelvins. But the temperature of the water is, we are told, 95, right? The degrees Celsius over here. So in kelvins, that's 368 kelvins. So we see that the temperature of the balloon is less than the temperature of water, okay? So, so the question is deduce whether the temperature of the air inside the balloon becomes equal to the temperature of the water during the expansion of the balloon. So no, okay, it doesn't. Question 15 now. Small lead spheres are added to a test tube until it floats vertically in a beaker of water, as shown. Okay. The test tube is displaced downwards and released. After release, the test tube moves vertically up and down with simple harmonic motion. The resultant force acting on the test tube is given by minus kx, where k is a constant. State what is meant by x. So x is the displacement from the equilibrium position. Okay, state the significance of the minus sign. Okay, so the force pretty much tends, so I'm gonna write it down. So the minus sign says that the force tends, to bring the tube back to its equilibrium position. And you can also say it's a restoring force. Restoring force. Okay, so again, my handwriting. So, restoring force. Okay. The test tube is displaced downwards through 3.5 centimeters and then released. Calculate the maximum kinetic energy of the test tube. And they give you the mass of the test tube and condense and the period of oscillation. Okay, so first of all, the maximum velocity is omega times a, right? And yeah, let's just keep it like that. So the kinetic energy max is equal to 1/2 mv max squared, or 1/2 m omega squared, and then the amplitude squared, right? So then we have to also convert omega to 2 pi over t, the period, squared, times a squared. And now it's time to plug in numbers. I converted omega because they give us the period, okay? So we have 1/2 times 18 times 10 to the negative 3 kilograms, because they give us mass in grams, okay? Times 2 pi over 0.64, okay? Times the amplitude, which is 3.5 centimeters. So that's 0.035 meters squared. So if we plug in everything, we find 1.1 millijoules, okay? Or 1.1 times 10 to the negative 3 joules. I hope this makes sense. And last but not least, the graph shows how the acceleration of the test tube varies with time. Okay, draw on the axis below a graph to show how the velocity of the test tube varies with time. Okay, there are many ways to do this. For this one, I decided to actually write down the equations. Okay, so what's the equation describing this graph? So A is minus omega squared A cos omega t. How do I know that? Because at time 0, cos of 0 is 1. So we get the maximum negative value. Okay, so at time 0 we are there. Then in one period we are also at the minimum, and so on and so forth. So that's the equation describing the acceleration. What's the equation describing the velocity then? It should be v equals to minus omega a sine omega t, because a is dv over dt, which is equal to minus omega squared a cos omega t, okay? So the graph for the velocity would look like this. Let's use blue. Okay, so it should look like, okay, so this is the period, right? So in one period we have to go from, let me see. Wait, I got myself confused now. Okay. So like this. Okay, so this is the equation for the velocity. Okay, it's not perfect, but it gets the spirit. All right, question 16 now. Some mags change color when the temperature of the mag is greater than a particular value. Okay, the photograph shows hot water being poured into a mug. The mugs are different colors because they are at different temperatures. Okay, as the hot mug cools down, it will change back to its original color. The mug is filled with water at temperature of 100 degrees Celsius. The graph shows how the energy E transferred to the surroundings varies with time t. Okay. Question A. The mug changes back to its original color when the temperature of the mug falls below 65 degrees Celsius. The instructions claim that after filling the mug with water at a temperature of 100 degrees Celsius, it will take 300 seconds for the mug to change color. Evaluate the accuracy of this claim. Ignore the specific heat capacity of the mug. Okay, this is a long problem to read. Okay. Okay, so first of all, we have to find, okay, in this process, how much energy will be released. Okay, so delta E is C of water times the mass of water times delta theta. And because they don't give us the mass of the water, we have to use the density of water. So C of water times the density of water times the volume times delta theta. Recall that density is mass over volume, so mass is density times volume. Okay, so if we plug in numbers, we have 4,200 times 960, which is the density, kilograms per cubic meters, times the volume, which is 3 times 10 to the negative 4 cubic meters, times delta theta. Again, this is the only case in which you can use delta theta. You can use Celsius and you don't have to convert because you're taking the difference, okay? So the same difference in Celsius is the same difference in Kelvin. That's the reason, okay? Okay, so the temperature change is 100 minus 65, that's 35. Okay, so the energy needed is 42,336 joules, which is 42.34 kilojoules. And now we can look at the graph. Okay, so 42.34, so that's 40, 50, 42, 44, 46, 48. So 42 is somewhere here. Okay, so maybe that value, which corresponds to, that's 270 seconds. Okay, so it will take less. Okay, so from graph, it will take, oops, am I running out of battery? Don't know. It will take 270 seconds, which is less than 300 seconds. Okay. Part B, the same mass of milk at a temperature of 100 degrees Celsius is poured into the cold mug. The specific heat capacity of the milk is less than the specific heat capacity of water. Explain how the time taken for the mug of milk to change back to its original color would compare with the time taken for the mug of water. No further calculations are needed. So it will take less time, right? So because you can see it from the graph, right? So because the specific heat capacity is lower, the specific heat capacity of milk is less than that of water, it will take less time. Okay, and the time will decrease as the rate of losing energy will increase. Okay, so it will take less time as the rate of losing energy will increase. Okay. Okay, question 17. In 1986, there was a major accident at the Chernobyl nuclear power plant. This was in Ukraine, by the way, for those of you, I mean, you guys are really young, so, I mean, I was a baby when this happened, so. Okay, there was a meltdown of the reactor core and radioactive isotopes were spread across a wide area. Two of the main isotopes released during the meltdown were cesium-137 and strontium-90. Both isotopes decay by beta emission. Complete the nuclear equation for the decay of strontium-90. Okay, first of all, the beta particle has a mass number of 0 and an atomic number of -1. Therefore, we know that this element Y, which is yttrium, by the way, okay, has an atomic number of 39. Okay, 39, and a mass number of 90. Okay, and by the way, for those of you who are curious, yttrium is used in cancer treatment. Check it out. I mean, it's irrelevant to the problem, but yeah, you can check it out. All right. B, part 1. Scientists have estimated that the cesium-137 released from the reactor had an initial activity of 8.5 times 10 to the 16 becquerels. Calculate the number of atoms of cesium-137 released from the reactor. Okay. Okay, let me check something because I think I took the long road. Yes, okay. This is what you need to use. Okay. So pretty much the activity is given follows the same rule as the radioactive decay. So activity is equal to the initial activity e to the minus lambda t, but A naught is equal to lambda times the initial number of nuclei, and lambda is 1 over the time constant, so that's equal to n naught over t. So let's go back to the problem. Okay. In the solution I see in front of me, the one I worked on myself, I think I took some extra steps that are not needed, so they might be confusing. So let's just use that A naught, the initial activity, is equal to the initial number of nuclei over the time constant, okay? So n naught is equal to the time constant times A naught, but they give us the half-life, right? So T1 half is ln of 2 over lambda, which is also equal to the time constant times ln of 2, right? So the time constant is equal to the half-life, which we are given, over ln of 2, or 1.37 times 10 to the 9 seconds to the minus 1. No, seconds, I'm sorry. You need seconds to the minus 1 for lambda. And I have a PhD in nuclear physics. This, I mean, shame on me. So anyway, I mean, you see, people make mistakes. So let's take this equation and find the initial number of nuclei. So n naught is 1.37 times 10 to the 9 seconds times the initial activity, which is 8.5 times 10 to the 16. So what do we find? 1.16 times 10 to the 26. Avogadro's number is 10 to the 23rd. So whenever you find numbers that are close to that, it makes sense. So actually this is 1,000 times larger, which corresponds to a few kilograms, maybe a kilogram of material or something like that. So it's not asked of you to calculate that. So okay, this is the initial number of nuclei. Part 2, scientists have estimated that the strontium-90 released from the reactor had an initial activity of 8 times 10 to the 15 becquerels. It is suggested on a website that the activity of the cesium-137 released from the reactor will take 1,000 years to become equal to the initial activity of strontium-90. Deduce whether this suggestion is accurate, and they give you 1 year in seconds. So the initial activity is 8 times 10 to the 15 becquerels for strontium-90, and the initial activity is 8.5 times 10 to the 16 becquerels for cesium-137. Okay, so A, actually the way I wrote it might be confusing. So we want to see what are we interested in? Okay, scientists have estimated that the strontium-90 released from the reactor had an initial activity of 8. Okay, so let's actually name this A. Okay, because this is the desired activity, right? And this is the initial activity of cesium-137. So we want to see how many years it will take for this nucleus to have this much activity. Okay, so we will use A is equal to A naught e to the minus t over the time constant, and we will take the ln as usual. So ln of A over A naught is minus t over the time constant. So the time needed will be minus the time constant and then ln of A over A naught. And if you plug in numbers, we have minus 1.37 times 10 to the 9, which is what we calculated earlier, times the ln of A is 8 times 10 to the 15, the desired activity, and A naught is the initial activity, which is 8.5 times 10 to the 16, and this cancels. And if we multiply, we find that this is the logarithm, so the ln of a number less than 1, so it's a negative number, it's a negative quantity. So negative times negative gives you positive, and we end up with 3.24 times 10 to the 9 seconds, which is equal to 102.8 years, which is much less than 1,000 years. So the claim is false. And now that we live in the era of AI and LLMs, and as you know, I'm really interested in AI and LLMs and artificial intelligence and machine learning and all these things, this is something to think about, because websites like this exist in the thousands out there in the World Wide Web, right? And the claim is that LLMs are trained using material from these websites. Okay, so sometimes they will spit out information like this that will look plausible, but it's going to be totally wrong. Okay, So I don't know if they will, if they found or if they will find ways to correct for mistakes like this. But LLMs are predictive machines pretty much. So they predict the next word in a text. And the next word is predicted based on the input, the initial input that they used for training. So if the training tells the LLM that information like this, it will spit out that information, which is going to be wrong. So it's always good to fact check, LLMs and anything else you use in life, okay? So let's move on. Okay, question 18. A Hertzsprung Russell HR diagram for a star cluster is shown. A, add scale values and a label to the horizontal axis of the HR diagram. Okay, so for the horizontal axis, we have the temperature in Kelvin, and it increases backwards. Okay, so let's say that if this is 2500 kelvins, then this is going to be 5000, then this is going to be 10,000, and then this is going to be 20,000 or something like that. I don't think they need precise values, but for the luminosity, they usually list the luminosity of the sun somewhere in the middle, and then 10 times the luminosity of the sun. So this is a logarithmic scale, right? And then 100 times the luminosity of the sun, and then below that you have 0.1 the luminosity of the sun, and maybe 0.01 the luminosity of the sun. Okay, I hope this makes sense. And here I'm trying to write L with subscript S, and actually I think I'm wrong. Actually, sorry to be doing this, but okay, if you want to be precise, I think the luminosity of the sun, I'm not an astronomer, but I think the sun is symbolized with that symbol. So this is 10 times the luminosity of the sun. This is the luminosity of the sun, 0.1 the luminosity of the sun, and then 0.01 the luminosity of the sun. Okay, so this means the sun, and I think the Earth is this. And many other planets have, I think Mars is like that. Don't quote me on that. Go check for yourselves. But back in the day, I used to like astronomy and read books about it. So I think that's how you denote it. All right, question part 2. Explain how the HR diagram shows that this star cluster is old. So we have some red giants over here. How do we know that they are red giants? Very high luminosity, very low temperature. Okay. Over here, we also have lots of white dwarfs. Okay, how do we know it's white dwarfs? Very high surface temperature, very low luminosity. Okay, and also over here, you see this area is empty. Okay, what's that area? That's the area of stars with really high temperature and very high luminosity. So these are blue giant stars. Okay, so those stars that shine the brightest burn the fastest. Sometimes people argue that this is true in real life as well. I mean, think about Amy Winehouse and I don't know, James Dean, stuff like that. But okay, this is not a movie or a music video, and please don't die young. I mean, it's not good. It's not a good idea. So, but anyway, so not a lot of blue giant stars because they burned. Okay. So this is an old cluster. Okay. So explain how the HR diagram. So in the top right, we have red giants. Okay. Bottom left, we have white dwarfs. Okay. And also we don't have many blue giant stars. Actually, we don't have any blue giant stars, but okay, maybe one can claim that maybe this is a blue giant. Okay, So yeah, let's move on. Part B, part 1. Arcturus is one of the brightest stars visible from the northern hemisphere. It is claimed on a website, again with the website, okay, that the radius of Arcturus is about 25 times greater than the radius of the Sun. Evaluate the accuracy of this claim. Okay, and they give you the luminosity of Arcturus. They give you the maximum wavelength of radiation emitted by Arcturus, okay, and the radius of the Sun. Okay, so here we will need, first we need to find the temperature. How can we do that? Wien's law tells us that the maximum wavelength emitted, actually the wording is wrong. It's not the maximum wavelength emitted. It's actually, no, my wording is wrong. I'm sorry. The correct way to describe it is that most light emitted from the star peaks at that wavelength. Okay, so let's find the surface temperature using Wien's law. So lambda max times the temperature is equal to 2.818 times 10 to the negative 3 meters Kelvin. Okay, and if we solve for T, we find 2.898 times 10 to the negative 3, and then we have 6.76 times 10 to the negative 7, okay, and then we have meters Kelvin over meters. Okay, so the temperature is 4,286.98 Kelvin. Okay, the luminosity is equal to sigma times the surface area times temperature to the fourth. Okay, so we are not given the surface area, so we have to calculate it. The surface area of a sphere is 4 pi r squared and then t to the fourth. Okay, so the radius is equal to the square root of L over 4 pi sigma t to the fourth, which is 1.65 times 10 to the 10 meters, which is, if we divide with the radius of the Sun, 23.69 times the radius of the Sun, which is less than 25 times the radius of the Sun, so not accurate again. I don't know if they do these things on purpose to show you that websites are not perfect, and therefore machine learning models are not perfect, and AI is not perfect, and so on. Maybe they do, I don't know. If anyone from Edexcel is watching, please let us know. Okay. Okay, now the second part of part B. Explain where on an HR diagram Arcturus will be located relative to the Sun. So the temperature of Arcturus is less than the temperature of Sun, which is about 5,000 degrees Kelvin. And also, the radius of Arcturus is much larger than the radius of the Sun, of course. So it's probably a red giant. So red giant area. So I would say it's somewhere, let's use orange. So somewhere here, okay, maybe, okay, somewhere here, okay, because also the luminosity is much higher. Okay, so this is Arcturus, okay, Arcturus, oops, Arcturus. And by the way, Arcturus means the bear in ancient Greek, okay? So, as a Greek speaker, as a Greek native speaker, I always feel obliged to to say, I mean, to speak out when a word is Greek and, you know, describe the meaning. I know I'm annoying probably, but yeah, okay. All right, so let me see, question 19. Let me see. Okay. The photograph shows a party balloon made from a thin material. The balloon is filled with helium, which is less dense than air. So A, explain why the balloon would accelerate upwards if released. You should assume that the mass of the thin material is negligible. Okay, so I'm gonna draw on the balloon, okay? So if this is the center of mass of the balloon, it will experience an upthrust and its weight, right? So two forces are acting, right? So what is the upthrust? The upthrust is going to be equal to the density of air in the balloon times the volume times g. So the upthrust is equal to the mass of the displaced volume, right? Which is, what's the displaced volume? It's the equivalent displaced volume of air, okay? Because, okay, this is the volume of air that the balloon displaces to be there, right? I hope this makes sense. So this is the mass of air displaced, okay? Which is equal to its density times the volume times g. All right, the weight is m times g, and the weight is actually the density of helium this time, right? Because it's the mass of helium. Oops. So mass of helium times g. So it's the density of helium times v. The v is the same as the v we use for the upthrust, right? Times g. Okay, so if it accelerates upwards, it means that the upthrust is larger than the weight. Okay, and so we can write that because the density of air is larger than the density of helium, right? There is a resultant force. There is a resultant upwards force accelerating the balloon upwards. Okay, so this is AS level physics, but you see, guys, sometimes they ask questions from AS level physics, so it's good to know these things. Okay, and now part B is a long writing problem. The helium slowly escapes from the balloon, so the volume of the balloon decreases. Okay, after some helium has escaped, the temperature of the helium gas in the balloon increases and the volume of the balloon starts to increase. Explain why the volume of the balloon starts to increase. Your answer should include reference to the momentum and kinetic energy of helium molecules in the balloon. Okay, so this is a little bit of a misleading problem. And it's misleading in that, you know, instinctively, you would expect that, okay, if some helium escapes, the volume will decrease and then the temperature will decrease as well, right? But they tell you that the temperature of the helium gas increases. Okay, we don't know how this happens. They probably assume that it absorbs some heat from the environment or something like that, but this is where you have to start answering the question. You shouldn't question this part. You don't care about this part. You care about this part and onwards, okay? So we don't care how the temperature increased, but since it increases, then let's assume that this is grounded and move on. So since 1/2 m times the square velocity of molecules is 3/2 kT. Then if the temperature increases, the velocity increases, and the kinetic energy increases, right? And is there anything else? And the kinetic energy increases for the molecules. Okay, let's write it like that. For the molecules. Okay. This will lead to more frequent collisions, between molecules, as well as molecules and the balloon walls. Okay. Okay. So the force on the balloon increases due to the more frequent collision, right? So the force on the balloon increases. Okay. Hence, the pressure, which is force per area, right, increases. Hence, the volume increases. Okay, I hope this makes sense. Moving on to question 20, I think. Is this the last question? Let me see. I think there is two more questions. There are two more questions. So, question 20. The graph shows how the binding energy per nucleon varies with nucleon number for various isotopes. Explain why a large nucleus such as uranium-235 releases energy during fission, but a small nucleus such as helium-4 does not. Okay, so if 235 uranium splits into two lighter nuclei, the two resulting nuclei have smaller nucleon number, okay, and hence larger binding energy per nucleon. Okay, and so energy is released. Okay, but if helium-4, if helium-4 splits, the resulting nuclei will have a smaller binding energy per nucleon than helium-4. Okay, so no energy will be released. Okay. Part B, question part 1. Show that the binding energy per nucleon of iron 56 is about 9 MeVs. They give you the proton mass, neutron mass, and the mass of iron 56. So, binding energy is given by, binding energy is equal to Z times the mass of protons plus N times the mass of neutrons plus mass of 56 iron times C squared. Okay, and this is a rare occasion in which I will just plug in numbers. I mean, there's nothing else you can do. So 28 times 1.00728 U, which is atomic, which is the atomic mass, plus 28 times 1.00867 U minus 55.93 49.44 U times C squared. And all these lead to 0.51166 atomic mass, okay, units. I'm trying to find it. Okay, so this is the atomic mass unit. One atomic mass unit is 1.66 times 10 to the negative 27 kilograms. So let's go back here. So we have to multiply that by 1.66 times 10 to the negative 27 times the speed of light squared. Okay, so this is 7.64 times 10 to the negative 11 joules. And if you convert that to MeVs, if you divide, so you divide by, okay, let me show you actually. So if you divide by 1 point, let's use parentheses. No, actually, I'm making things complicated today. I don't know why. So if we divide by 1.6 times 10 to the negative 19 joules per electron volts, this becomes 477.76 MeVs, which is, let me write it down there. Okay, no, let me use a clean page. Okay, so if we divide, so B binding energy over number of nucleons is 477.76 over 56, which is the mass number. This yields 8.53 MeVs, which we can stretch to be about 9 MeVs, okay? And that's the answer. Part 2. Determine a value for the binding energy per nucleon of uranium-235. You should use the graph. Okay, so I did use the graph, and I assumed that one of the squares, so this square corresponds to, so this is 1 MeV, I assume. So that's 1, 2, 3, 4, 5, 6, 7, 8, and that's 9. Because you can see that the iron 56 is somewhere there, which is 8.5 that we found. So if my reasoning is correct, this is 7 and this is 8, so 7.2, 7.4, about 7.6, so maybe 7.5, something like that. So, I mean, this is uranium-235, and it corresponds to about 7.5 maybe MeVs, okay? So B over A for, what was it, uranium-235 is about 7.5 MeVs. That's the answer. Okay. 21. Astronomers use a variety of methods to determine the distances to astronomical objects. A. Describe how trigonometric parallax is used to determine the distance to nearby stars. Okay, I can write it in words, but I always like to draw a scheme. I think it's easier to understand. So if this is our beloved sun in the center, and this is our planet, okay, so this is the Earth, and it goes around the sun. In 6 months, it's going to make it all the way down here. So this is the Earth, and this is the Earth 6 months into the future. So I'm going to draw an arrow there. So in 6 months, okay, the distance from the Earth to the sun is 1 astronomical unit. Okay, and let's say that there is a star. Let's use orange. There is a star over here at the distance d, and we want to know that what d is. Okay, so you observe the star now. Okay. Oh, and behind this star there is a background of stable stars that are not moving, of stable stars, let's say. Okay, let's make them green. I don't know why. So this is the background. Okay, actually let's make them a little bit different. Okay, oops. So these are stars. Okay, so if I'm standing here on the surface of Earth now, I will observe the star and I will observe these stars behind it. Okay, and 6 months into the future, if I observe the same star, I'm gonna find that behind that star I see now different stars. Okay, so excuse me, so there is a parallax. Okay, so this is the parallax that we see. Okay, so we see the star kind of moving, right, as we observe it at different times, and we can calculate that angle, okay, which you call parallax. So the answer in words, actually, though, is that the star we are interested in is observed now, against a background of stable stars in a 6-month interval. Okay, the angular displacement is determined okay, so using the known distance between the Earth and the Sun, which is 1 astronomical unit, and trigonometry. Okay, I'm gonna move to the clean page. So, and trigonometry, D can be determined. All right, this was a long problem. Okay, so part B, astronomers can use observations of type 1a supernovae to determine the distance to nearby galaxies. A type 1a supernova is an exploding white dwarf star. Give two properties of a white dwarf star. Okay, it has high temperature, low luminosity, a small radius. Okay, they ask for two, I'm providing more. Small radius, and there's no more fusion going on. No more fusion. Okay. Type 1a supernovae are examples of standard candles. Describe how astronomers could use observations of a type 1a supernova to determine the distance to nearby galaxies. So standard candles the quality of my handwriting deteriorates as the time moves on. I'm doing this on one sitting, so you get tired. So standard candles have known luminosity. Okay, so we need to measure the intensity of radiation I on Earth. Okay, and since I is L over 4 pi d squared, d, not d squared, okay. D squared is a brand, right, of clothes, I think. So D can be determined. Okay, we know the luminosity. Okay, so that's I. I'm sorry for the terrible handwriting. Okay, so that's I, and that's also I. Okay. C. The Landolt NASA space mission planned for 2029 will use lasers on a small satellite to direct light towards the Earth. The satellite will appear to be fixed in place in the night sky, as it will be in an orbit above the equator with an orbital period of 24 hours. These are also known as geostatic, I think, satellites. I think I mentioned it in one of my lessons. Anyway, calculate the height of the satellite above the surface of the Earth. Okay, so the gravitational force, the gravitational attraction from the Earth is what provides the centripetal force for this satellite. So let me use a clean page. So I'm trying to say is that if this is the Earth and this is the satellite, okay, then there is a gravitational, so the satellite moves this way, and there is a gravitational attraction given by G times the mass of the Earth times the mass of the satellite over r squared, where r is the distance from the center of the Earth to the satellite. Okay, so the center of the Earth, not the surface of the Earth, the center. Okay, so this force is what provides the centripetal force. So G times the mass of the Earth times the mass of the satellite over r squared is m omega squared times r. M cancels, and we get gm equals to omega is 2 pi over so omega is 2 pi over the period. So if we take the square, this 4 pi squared over t squared times r cubed. Okay, so r cubed is, sorry, actually just R. So R is the cubed root of g times the mass of the Earth times t squared over 4 pi squared, and I will need to move to the clean page. So this is a giant root, cubed root. Okay, so g is 6.67 times 10 to the negative 11. The mass of the Earth is 6 times 10 to the 24. The period is 24 hours times 60 minutes in an hour times 60 seconds in a minute squared. And then we have 4 pi squared in the denominator. This gives us 4.23 times 10 to the 7 meters from the center of the Earth. So R is equal to the radius of the Earth, right? You can see it over here. So this is the radius of the Earth, and this is the height from the surface, right? So R is equal to the radius of the Earth plus the height from the surface, and this is equal to 4.23 times 10 to the 7 meters. And if we solve for h, we have to subtract the radius of the Earth from 4.23 times 10 to the 7, so we find 3.59 times 10 to the 7 meters, and that's our answer. Okay. And part 2 suggests how astronomers could use light from these lasers to calibrate light detectors on ground-based telescopes. So we can say that lasers will have a standard luminosity, so they will be sort of like standard candles, if that makes any sense. So lasers will have standard luminosity and distance, right? The distance is also known. And distance. Okay. So they can be used as standard candles for calibration. Oops. Calibration. Okay, and this was the Unit 5 October 2025 test. I'm gonna check out the Unit 5A, and if it's different from this test, I'm gonna also upload a video hopefully soon, probably within this week, we will see. So I hope these videos are useful. Good luck, guys, with your exams. Let me know if you have questions in the comments. I always look at the comments. I mean, the channel is really small, and I need your help to get it growing. So please like these videos, subscribe, tell your friends, and I don't know, something like that. And yeah, okay, I'm gonna see you in the next video. Bye.